Okay, hi. This video, I want to talk for a few minutes about earthquake sizes. So we're going to need to understand earthquake sizes and the difference between a big and a small earthquake quantitatively. And so we're going to talk through some metrics for measuring that size and what exactly we mean by the size of an earthquake as well. So to get started, I've got a screenshot up here from a news report, and this probably looks somewhat familiar to you. I would guess you've heard of the Richter scale in some form or the other in the past, and the news media really likes this Richter scale, right? So you oftentimes see, there's an earthquake somewhere in the world, and it was 5.6 on the Richter scale. So this Richter scale is actually an obsolete scale. It does exist, and we'll talk about it in a second, but it's not used anymore by. All right, so this Richter scale does exist. We'll talk about it in a minute. So this earthquake scale does exist. We'll talk about it in a minute, but it's obsolete from the perspective of seismic hazard and risk analysis. It's not used, or it's used only in kind of last resort situations. So that's one thing to consider. When you hear the news reports about Richter scale, it probably wasn't actually measured in the Richter scale by scientists, but somehow that persists on. The other thing that's problematic here is this table here down to the lower right kind of relates magnitudes of earthquakes, which is a metric of size, to the impact of the earthquake. And that relationship is not the case either. We're going to move into ground motion produced by the earthquake, and that's usually what's producing the impact, or perhaps a tsunami or something else. But a magnitude 8 earthquake in the middle of the Pacific Ocean is not going to cause any impact. Right? The location of the earthquake, it matters a lot in terms of the effects that it produces at the surface. So takeaway here, I guess, just to get us warmed up on earthquake sizes is when you see these media reports, shortly here, you're going to understand why there's a lot of incorrect language and concepts used oftentimes in those media reports. Okay, so let's talk about Richter scale just for a moment. So this is more formally known as local magnitude in the kind of earthquake science community and earthquake engineering community. It comes from a paper written by Charles Richter, who was really a pioneer in seismic hazard analysis, things like that. So the original paper that proposed this scale was written in the Bulletin of the Seismological Society of America. And this is the first page of it over here on the right. Note the year. So this was proposed in 1935. Quite pioneering at the time, but in almost a century that's passed, we've, of course, advanced our knowledge and our data quite substantially. So what Charles Richter proposed was to, when we're looking at an earthquake, we'll look at the amplitude of the signals on a seismograph, and that's the kind of era of seismograph in the lower right here that he was working with. So these analog instruments that were recording squiggles on a piece of paper. You might have seen those somewhere or the other. Mostly now they just exist in museums. But you would take the amplitude off of that squiggle, and then you would do a conversion to see how far away the earthquake was. And the bigger the amplitude, the bigger the magnitude. And so he created a scale to go between. And so he did this work for Southern California based on a set of observed earthquakes and ground motions. And the formula here is down in the bottom. Right, so he says that this ML, which is the local magnitude, is going to be a function of the base 10 log of the amplitude that we see from this seismograph, and plus a coefficient times the base 10 log of the distance, how far away the earthquake was. So, if it was further away, you would expect a smaller amplitude for the same size of an earthquake. And then a constant as well. And so this 2.56 and the 1.67 that he proposed, those were empirical coefficients. So he just did some fitting to kind of move from amplitudes to this numerical scale of magnitudes. And those coefficients, they depend on the region that you're in. So that's why this model is for Southern California. Somewhere else in the world, the ground motions are going to propagate through the earth differently. And so the same size of an earthquake could produce different amplitudes. Also, these coefficients depend on instrument. So if you're using a different seismograph, you're going to have different amplitudes. And so you would need some different coefficient as well. All right, so this was kind of this empirical fit. And so what he did was make this interesting relationship between the amplitudes and the size of the earthquake. So this fit is going to only work depending on the kind of frequencies of the earthquake, and that relates to kind of what the seismograph was detecting. And it's only valid for certain distance ranges as well. So if you get too close to the earthquake, you can't tell the differences, or if you get too far away, the amplitudes do other complicated things. So you had this equation, and it had to be calibrated per region, but it did give us this idea of putting the size to an earthquake. It's also quite easy to apply. So as long as you have seismographs and you can measure amplitudes and you can locate the earthquake so you know how far away it was, then you can use this formula to estimate an earthquake size. Quite easy, and it does still get used in certain circumstances we'll talk about later, just because of how easy it is. But really the state of the art for earthquake sizes, we're going to use seismic moment instead. And the idea here is rather than look at the amplitude of shaking that you observe some distance away from the earthquake, let's actually measure the energy released during the earthquake. So that's a much more fundamental scale to say, well, when this earthquake occurred and this slip happened, how much energy was released? And that'll show up in shaking amplitudes, but it shows up in other ways as well. And this will be more robust. Okay. So the idea with the seismic moment, and we're going to typically denote that m subscript 0. That's a very common notational convention. We're going to use this integral here, and let's talk about what's in it. So the first thing that's in this is a shear modulus. And so you might remember from mechanics days or things like that. This is measuring kind of how much energy it takes to kind of slip the material by some amount. And the x is a coordinate across the rupture plane. Right? So that's kind of an energy per unit of slip. Then the u is going to be the amount of slip. So at each point on the rupture, how far did it slip? And then we're going to take the shear modulus times the slip, which is kind of a work per area, and we're going to integrate over the rupture area. Okay, and to help kind of think about this visually, I know these integrals are a little hard to process the first time you see them. Down in the lower right here is a figure of a numerical model for earthquake slip from a past earthquake. Okay? So what's going on here is we've got kind of a map of the surface showing, and then this rectangle here is a mathematical model for what happened in this earthquake. And so we've got this rectangle showing kind of the boundary of the earthquake, and then the coloring on the different grid points is the slip. So there's kind of slip from 0 up to 3 meters or so, according to this numerical scale. And so what you could think about is each one of these grid points being like one of the dAs in this formula. And we'll say at each point here on this rupture area, we've got an amount of slip that's indicated by the color, and then we'll have a shear modulus, which is indicated by kind of the material properties, right? So that's just a metric of material, just like we have a modulus for steel or something like that when we're doing structural engineering. Okay, so that's the basic formula, is just kind of how much work is, or how much energy is released per unit area, integrate up over the whole area, and that's the total energy released during the earthquake. All right, so that's the fundamental concept. Then we'll make some simplifications here. So the first thing we'll do when moving from line 1 to line 2 is we're going to assume the shear modulus is constant in space. All right, so this is a material property. It's a kind of a crustal interface material. We don't have any kind of direct observations of these shear modulus. We have to get kind of typical values in a bulk sense. And we don't need to assume it is constant in space, but the typical convention is to assume it's constant in space. And actually we could jump ahead. So this shear modulus, so we'll just call it mu rather than mu as a function of x. And our typical value for kind of crustal rock is going to be 3.3 times 10 to the 10th Newton per meter squared. Okay? So that's just a typical value used very widely. We can just note that coefficient down and use it. It's rare that we have any sort of deviation from that. Okay, so that's the first assumption. Then what we're left with is kind of in the second line here, we've got a slip per unit area, or slip as in space multiplied by these little dAs, and we add them all up. So that's actually equivalent to the area of the rupture times the average slip, right? So if we just took an average slip, we can simplify down. And so that's just the operation here that's going to be left over is the area. Let's note that, I guess. So this is area, and it's going to be, let's see, of the rupture. And this is going to be in meters squared, typically. We just have to watch for consistent units. The ruptures can get quite big. Units of kilometers would be natural, but just for watching unit consistency, you can see that the shear modulus was newtons per square meter. So we've got times meter squared. And then this mu bar is going to be the average displacement, or average slip, over the rupture. And that's going to be in units of meters. All right, so we're going to end up with a moment, seismic moment in units of newtons times meters, if we look at kind of how the meters units all cancel each other out. Okay, And so Newton meters will be our metric of seismic moment. And maybe just to close out this idea, so the integral version of this seismic moment is going to take that picture on the lower right. We'll take the slip values per grid point here, the kind of color scale, and we could multiply those by the size of the grids, the DAs, and add them all up. Alternatively, we could just say, well, the area of this big rupture is the A, and then the average slip would be kind of the average value of all those colored grid points. And so the average slip might be a half meter or something like that in this case, or a meter. And so the 1 meter times the dimension of the rupture would be the easy way to compute the seismic moment. And that's mathematically equivalent to doing the integral over space. So in general, these earthquakes are going to have variable slip, right? There'll be patches of high slip and patches of low slip. But also of interest to us is just going to be the average slip or the average displacement for the purposes of computing things like the seismic moment. Okay, so that's seismic moment. And then, so if that's a kind of a fundamental metric of earthquake size, the magnitude scale we're generally going to work with these days is, or the kind of preferred magnitude scale we'd like to work with is the moment magnitude, right? And so this is a scale that's going to map those seismic moment values from the previous slide into a numerical scale that's very similar to the Richter magnitudes, right? So this is Tom Hanks and Hiro Kanamori in 1979 proposed this scale. And they said, look, people are familiar with this Richter scale, so let's kind of keep the numerical scale in the ballpark of the same, but let's use this more fundamental metric here. So in 1979, they proposed this idea. They called it MW. And so this is our moment magnitude. And they used this seismic moment, M0, from the previous slide, and they did this conversion. They said, well, let's take this log 10 of it, and then the 2/3 and the 10.7. Those are just coefficients that are going to approximately match the Richter scale, or the ML scale. Okay, and maybe just for completeness, this M0, let's note that has the value from the previous slide. Okay. So one, just historical reconciliation here is that the original Hanks and Kanamori paper used moment magnitude in units of dyne centimeters. So that's the note here in red text. And 1 dyne centimeter is 10 to the 7 Newton meters. So there's a unit conversion here. These days we work in units of Newton meters, as I explained on the previous slide. And so it's actually not too hard to take the conversion. You take the 10 to the 7 outside of the log 10, that just becomes a constant. And so it turns the 10.7 constant into a 6.03. So the second one is the equation that we use. So that's the one to save and do your calculations off of, because it's using the modern units that we work with. Okay. It's a couple notes here at the bottom. So originally this moment magnitude scale, they were using this MW. That was pretty popular, indicates work done. So it's kind of this energy work concept. Oftentimes now we'll use a boldface M. And so that's kind of written down at the bottom. And then also a common approximation is instead of using a 6.03, we'll just use a 6 as the coefficient. So that's the bottom equation down there. So if you see that, that's kind of how this equation developed from the historical paper from several decades ago. Okay. So this is our preferred metric. For big earthquakes, we're going to compute this moment magnitude, and that's actually what's typically reported by scientific agencies. It just gets called Richter magnitude because of a news media convention. It's not actually a Richter magnitude or an ML magnitude most of the time. Okay, so let's try putting this to work and just do an example calculation. So I've got here some values for the Loma Prieta earthquake in 1989. A rupture length and a rupture width. So we know the dimensions of this thing. And then across that dimension, the average lateral displacement was 182 centimeters. So that's enough information for us to compute a moment magnitude. And I'd encourage you to pause the video for a second and do this calculation yourself using the previous couple slides. And then you can unpause and see how I do it. Okay, so the first thing we're going to do if we need to compute a moment magnitude is we need to compute a seismic moment. And we'll use the bottom version of the equation from the seismic moment slide. So we'll take the shear modulus times the rupture area times the average slip. Okay. Shear modulus, we're going to take that standard value, 3.3 times 10 to the 10th newtons per square meter. The rupture area is just going to be the rupture length times the rupture width. We'll need to do some conversions here because those rupture length and rupture widths were in units of kilometers. So let's say 1,000 meters over 1 kilometer is kind of unity. So I can multiply by that ratio, and then I'll square it. That'll get rid of my kilometers units. And then the average slip, we've got 182 centimeters. And here we'll have to do another conversion. That 1 meter is equal to 100 centimeters. Okay, so let's do a little bit of annotation here. So we've got the mu, we've got the area, we've got the average slip, and then just our unit conversion. So we've got kilometers, kilometers squared that'll cancel, and we've got centimeters and centimeters that'll cancel. So we're left with newtons per square meter, area in meters squared, and slip in meters. So we've got our units worked out here. And this is a common thing we're going to see with these earthquakes. So we've got kind of very broad spatial scales we're working with. So the rupture sizes are often, most natural in units of kilometers. The slip amount is going to be much, much smaller than the rupture dimension, here in units of centimeters. And so we'll have to do unit conversions to move back and forth and get things all sorted out. Okay, so at this point, we can put this into a calculator. We end up with 2.94 times 10 to the 19th Newton meters. Okay, and now we'll do moment magnitude. So we'll say M. And that could be a boldface M, or maybe I'll just write MW here to be kind of clear since I can't write boldface very easily. So this will be 2/3 of the base 10 log of 2.94 times 10 to the 19th. And I got my units right in here, minus 6. And we end up with MW equals 6.97. So about a magnitude 7 earthquake. Okay, so that's how we compute a moment magnitude. Let's see. So let's talk a little bit about magnitude scales or size scales. A couple other items here. One thing to keep in mind is that there are some other magnitude scales. I would say moment magnitude is going to be kind of the king magnitude scale. We'd really prefer that one. It's the gold standard. There are a bunch of other scales, and local magnitude being the most famous of them. And the other scales are going to look at, amplitudes of radiated waves as well. They may look at different frequencies or do slightly different things. But mostly it's going to be looking at amplitudes of the ground motion that we feel or that we measure and trying to convert that back to a size. And so here on the right, we've got a plot, and the moment magnitude is on the horizontal axis, and then the other magnitudes are on the vertical axis. And so a 1-to-1 line would be just plotting moment magnitude here. So ML, the one that we kind of talked about in most detail, is in the heavy black line. So you can see that one. Basically, it's sitting exactly on the 1-to-1 line down for lower amplitudes, up to a magnitude of about 6. It's exactly on the 1-to-1 line. So that's, really what was tried to achieve with the initial calibration between the two. So we could note here, ML agrees for magnitude less than 6. All right. As you get to bigger magnitudes, the 7s and 8s, we call this a saturation. So basically the amplitudes of the radiated waves are not increasing proportionally for these very large earthquakes as they do for the smaller earthquakes. And that's largely because portions of the rupture are further away than other portions. And so the radiated waves don't kind of continue scaling in a simple manner. And so it gets hard to distinguish these very, very large earthquakes just by looking at the size of the waves at some station. So this is called a saturation effect, or the scale curves over. The other colors are some other scales. There's these body wave magnitudes is the B, or JMA is the Japanese Meteorological Agency. They have a scale as well. You can see they all kind of have the same general pattern that they track reasonably well with moment magnitude for smaller size earthquakes, but they all kind of curl over and start becoming more horizontal at very large earthquakes. Just using amplitudes of radiated waves is not a good way to infer the size of large earthquakes. That's a challenge. A couple other things about this conversion here. This type of plot is going to require some scales that vary by region. As we talked about earlier, the region is going to have some impact on the amplitude of shaking. It doesn't have an impact on the seismic moment or the moment magnitude, but it does on the amplitudes that we're using with the other scales. There's also some uncertainty in the conversions between them. Just keep that in mind. We're not going to get into the conversions here, but the important things to take away is that there's more than one way to measure the size of an earthquake. When you look at a catalog of past earthquakes, oftentimes we'll have recordings of different earthquakes in different scales. So the large earthquakes should be in moment magnitude scale. The smaller earthquakes might be recorded with a local magnitude or some other scale, partly because the scales agree well, and partly because it's just difficult to get the information needed for a moment magnitude for lots and lots of small earthquakes when there's tens of thousands or hundreds of thousands of them. And so we need to pay attention that there are different scales, and we have to do these conversions. It's not something that basic analysts need to worry about too much, but it's important to be aware that those conversions do have to take place. Okay, so I think that's a good place to stop here. That's the kind of the fundamentals of measuring earthquake sizes and computing these moment magnitudes, which will be important for us in later calculations.